Muxworthy, who will be speaking on the effects of stress on paleomagnetic signals. So thank you, Adrian.
Okay, well, thank you very much for the invite. I'm going to be talking about the effect of stress on paleomagnetic signals. This is a sort of new topic for me. I never really worked with stress before. It's something I started working on. There's a guy called Tom Mitchell, who actually studied at Liverpool as undergraduate with Max many years ago. And Tom does rock mechanics and he does earthquakes. He doesn't know much about magnetism. But anyway, he approached me a few years ago and he had this data from a fault in Japan. And he'd measured magnetic susceptibility. I'm not really quite sure why, but he'd measured magnetic susceptibility as a function of distance from the fault over up to 5 kilometers away. So quite a long way. And he got this increase in the magnetic susceptibility. And so he kind of approached me and said, why is there an increase in magnetic susceptibility? And I had to say, I don't really know at the time. And so we started kind of working together a little bit. I'm currently actually on sabbatical at UCL. It's very close to Imperial. It's only 20 minutes on the subway. So I'm on sabbatical, but spending actually quite a lot of time at UCL at the moment, working together on this. So this is sort of a summary of some of the work we've been doing over the last year. It's very much work in progress. Oh. Bit odd. Let me use a clicker.
Oh, can you? Thank you.
Oh, there we go. Okay. Okay, so I've done some work before on looking at stress in meteorites, but we've been doing very high impact experiments and looking at that. And when you've got very high impact experiments, we've got pressures up to multiple gigapascals. And essentially what we're doing is completely destroying the rock, and we're looking at the magnetization that's recorded. And in those cases, it tends to be due to thermal heating. So rather than looking at sort of shock and stress effects, essentially looking at thermal remnants effects. So even though I have done some work looking at squashing rocks and measuring magnetization, it's always been at much higher pressures. And what we're doing here is we're actually looking at a distance away from the fault itself. So at the fault itself, you get pseudotacholites forming, you get heating, you get melting of rocks. And a lot of people have studied the magnetic signal of that. But what we're interested in, and Tom was interested in, is looking at things quite some distance away. So rather than being in the zone here where everything's broken, so this is the classic kind of strain stress diagram, which I presume most of you are familiar with from physics at some point when you were undergraduates or so. And so rather than looking at this failure region or where you get plastic deformation, we're actually way down here. We're down into this linear section here. So essentially you squash a rock and then you release the stress, and essentially goes back again to its original state. And apart from a few cracks which have closed up, there's very little obvious damage to the rock. So we're in a zone where the effects are quite different to the sort of high pressure stuff that maybe some of you are familiar with. Okay, so looking at something new, as I said, I've never really worked with stress before. So as with many of you, when you're looking at something new to you anyway, the first port of call is David and Özden's wonderful book that I'm sure we've all looked at a few thousand times over the years, and to get some inspiration, understanding of stress. And I know people have worked on this for a very long time, so it's new to me, but not new to everyone else. And I've taken just from, there's only equation I'm going to show. This is an equation from David's book, and you can see this is the energy for a single domain particle. And essentially what we're doing here is adding in this stress term. And the theory behind single domain behavior has been around for a very long time, since the 50s and 60s. And essentially it's very simple. You have a single domain grain, you have zero stress, the magnetic moment pointing in the direction. You apply a uniaxial stress in this case, and the magnetic moment rotates away from that direction into the plane of the stress. Okay, so this is for a simple uniaxial stress. And if you look at the energy balances, you can do a quick back of the envelope calculation, which I've done here, where you look at the energy due to the sort of elastical stress effects over the demagnetizing energy, and you can make an estimate of the kind of values that you need to apply in terms of pressure or stress for the magnetic restriction to start dominating the anisotropy, and you get values of 1 or 2 gigapascals. So just try and keep that number in your head at the moment. So 1 or 2 gigapascals is the sort of typical values you might expect from back of the envelope calculation for single domain theory. Okay, so in addition to looking at David's book, David and Özden's book, I started looking at literature, and it's new to me. I didn't realize quite how much literature was out there on stress and magnetism, paleomagnetism, and people have been squashing rocks and measuring the magnetic properties for a very long time. The earliest paper I could find was Kalashnikov and Kapitsa from 1952, and Valery Sherbakov very kindly sent it to me. Unfortunately, my Russian isn't good enough to read the paper, but I can look at the figures, which is nice. There's a whole range of other papers, and I just picked one at random. This is from Keen et al. In 1976. So a lot of people looked at magnetic susceptibility. So what happens when you squash a rock? What happens to susceptibility? People measure that. Now, most of the measurements done in the 60s and 70s were done under stress. So they would squash the rock and then have an instrument that allowed them to measure under stress. Okay, so this is just a typical example. And a lot of the studies were done on very large multi-domain grains. Now, of course, as paleomagnetists, we're interested in not just the susceptibility response, as we show now, we're interested in the change in direction in any paleomagnetic recording. So we're interested in the magnetic remnants. And so here's a classic study from Nagata. Nagata did a lot of work in the 1960s on this. And here we have the effect here of, on this graph here. So we've got the in the stress state and the zero state. So essentially squashing the rock, measuring the magnetization, and then going taking it off and measuring out of stress, and then repeating that. You see there isn't so much deviation. But look here, that one of the things I want you to notice here is the pressures we're looking at here. So 1 gigapascal is something, so 1,000 MPa is the sort of typical value you might expect for single domains to be strongly affected. Now, I've chosen another example. I mean, there's lots and lots of studies. I've just chosen another one. I've chosen a more recent one from Mike Volk and Feinberg, and looking at the effect of the magnetization and applying various stresses at various temperatures. Just sort of pick this one relatively random, but the key point is you're getting changes to the magnetization at relatively low pressures. So there seems to be a bit of a disconnect between the single domain theory that's being used to describe the response and the actual experimental observations. Now, people have said in their papers, well, you know, it could be due to PSD effects, or depending on when the paper was written, or single vortex effects, but it doesn't really matter because single domain particles are the main carriers of the remnant. So we're just essentially seeing multi-domain effects on top, and that's not important. However, we know that rocks have single domain particles and single vortex particles. Okay, so we have these electronography images that we've not published, but we've shown some. This is a nice single particle, a single vortex behavior. And then for Andrew's going to accuse me of blasphemy, but I'm showing a day plot here with just a summary of some basalts that we've measured in my lab over the last X years. And you can see that, you know, whilst some particles do plot in the single domain box, the vast majority do not, which suggests the magnetization is dominated by single vortex particles. And we think that single vortex particles are ubiquitous in samples. So that just suggests that from this particular diagram. But I guess the key thing is, it's not that single vortex particles and bigger multi-domain particles are ubiquitous. We all know that. It's more the findings of the work that Les and Wynne and myself and some other people published in the last few years. And this is something that I think Andrew was just alluding to earlier, this particular diagram, where in this particular diagram, we've calculated, so we've got classic single domain theory here. This is the blocking temperature for single domains, obviously up to the point where single domain theory is no longer valid. And you can calculate, that's the black line, you can also calculate using nudge elastic band, the blocking temperature for, this is single domain. Then we get into a zone where we've got this sort of easy vortex kind of structure, which isn't very stable. And then you get into the single vortex ratio, so looking at grains greater than 100 nanometers, and you can see the stability is much higher. And if you calculate the relaxation time at room temperature, you can also see that the relaxation time is very high. And when we get into this sort of single vortex, true single vortex, we can see that it just shoots off way off the top of the screen, so much longer than the age of the universe in terms of the stability. So this kind of work that we've done, I think in an ideal way, demonstrates that actually single vortex particles shouldn't be dismissed. They're actually probably the main carriers of the magnetic remnants. Now, of course, this work is all for symmetric particles, and if you've got elongated particles, things might be slightly different. But the take-home message from this work is that we can't ignore single vortex grains. Okay, so there's kind of earlier theories dismissing when looking at stress are probably a little bit incorrect to just dismiss this non-single domain behavior, do single vortex grains and saying it's not important when we think it is. So we've very simply put the stress equations into MERRILL, and just to summarize what we're doing here, we have plotting the directions of the magnetizations for individual grains. So we have the direction at the top there, we have the stress axis, obviously got 2 points because it's a stress axis plotted on these stereonet plots. And then we calculate the direction of the magnetization, both the red increasing stress as we go up from the bottom to the top. In red, that's the magnetization direction under stress, and then we do the same for the remnant. So essentially we apply stress, it's very simple, apply stress, look at the magnetization direction, switch it off, look at the remnant's direction. Now you can see if you apply the stress in a single domain particle along that exit there, along the short axis, essentially the magnetization does not change. And that's exactly what we would expect to find. So at least our model is working correctly. And if we apply the stress for a single domain particle, this is 50 nanometer particles, you can see that, so applying it along the long axis, you can see that the remnant's direction, the blue one, does not change direction with time, with increasing stress, but the in-field, so the in-stress state rotates and then rotates back again. Okay, so this behaving exactly as we will want to. Now, we're not that, single domain grains are not the main focus of this, but of course you have to look at single domain grains. So we're really interested in single vortex particles. So what we have here is a 150 nanometer grain, and we have the vortex state and the pre-stress state. Then we apply stress along this direction here, along this particular direction. Vortex, which carries the magnetic moment, rotates into the direction of the stress axis here. And then when we switch off remove the stress, we end up with the magnetization doesn't flip again. So essentially we've rotated the magnetization. Well, you might have noticed that this means that we have the exact opposite trend between single domain and single vortex behavior. So single domain behavior on the left there, the magnetization rotates away from the stress axis, but single vortex, where the magnetization actually rotates towards the stress axis. So we get exactly the opposite response depending on single domain and single vortex behavior. Of course, you can have more exotic states where you're actually not just rotating the vortex, but you're actually nucleating and denucleating vortex states within our system as we change the pressure. So we start off here with we have a single domain state with in an 80 nanometer grain. So that puts us up here. Can you see the mouse? Yeah, it puts us up here in this zone here where it's relatively unstable. And when we apply a stress, it flips into a single vortex state. So that's a single vortex. We only need a relatively low stress, only 60 megapascals, it's quite low. And then when we increase the stress again, it flips again and goes into a single domain direction, a single domain state, and you can see it's rotated again. So it can be quite complex if we start changing domain states by the application of stress. Now, did a whole range of models, and this is just a summary of all the results. And what we're looking at here is the stress that's needed to change the remnant's direction. And you can see we did small particles, single domain, up to 80 nanometers in that zone where things are unstable, and up to 200 nanometers. And we don't have many single domain particles. That wasn't the main focus of our study. But the take-home point here is that we're actually looking at very low stresses here. Most of the particles are affected by stresses which are less than 200 megapascals, which is significantly less than the sort of back of the envelope calculation of 1 gigapascal. And this is important because it puts us here, and going back to our stress strain graph, it puts us here into this linear elastic zone here. So we can apply stresses to the rocks in theory, we can change the magnetization direction, and you would not actually be able to see that in the rock itself. Okay. So I had a look at the literature and looked at paleomagnetic results, studies around faults, and there haven't been that many. There's one from Saliards and Kirschvink from 1992 looking at the San Andreas fault, and they looked at the declination as you go away from the fault. So the distance here is quite small. It's only up to 50 meters. Remember in the diagrams I was showing earlier, the data was up to 5 kilometers. This is a much smaller scale. But the point is you can see small deviations in the declination as we go distance away from the faults, a little bit similar to the results we showed earlier. Now, in their paper, they did not associate this with deviations due to stress, they associated due to rotation. So there can be different interpretations on the data, but if we just say it could potentially be due to stress. Now, let's go back to susceptibilities. That was directions, but let's go back to susceptibility. And this is the original plot I showed you. If we look at other data from around the world, here's an aeromagnetic map from a fault, an earthquake in Malawi in 2009. And you can see around the fault, there is a strong magnetic signal. And you could associate that with stress. I mean, that'd be our interpretation. Of course, you could also associate it with cracking and fluids going in and increasing the magnetization. So it doesn't have to be stress, but one interpretation, it could be a stress effect. And when you look across the literature, there are other examples of this sort of effect in the literature. But very few paleomagnetic studies across faults. So we decided to do some of our own experiments. Now, some of these experiments are a repeat of what we've done before. And this is the very first one. We just simply get a rock and we just squash it in the laboratory and measure the magnetic susceptibility. So I plotted it stress on the vertical axis and susceptibility on the x-axis, so we can mirror the shape of the stress and strain of the sample and the actual measurement itself. So this is our sample going backwards and forwards and increasing the strain and stress in the samples. And then this is the susceptibility response. You can see the curve kind of almost matches. We're in the elastic zone here. So it seems to match very well. And if we plot one against the other, we can see we get almost a straight line between magnetic susceptibility and strain. Okay, so we were getting excited and we thought we will potentially, can we just use susceptibility as a paleo stress indicator? This would be quite cool. Apparently, in the earthquake community, this is a holy grail, is finding, can you estimate paleo stresses on earthquakes that are maybe a few thousand years old? It's very hard to do, apparently. Now, unfortunately, so this is not entirely new. People have done this before. I'm not claiming to be the first person to do that. But I should stress that we're doing everything after the release of pressure. If you look at the literature, I guess 90% is under pressure. So slightly different to a lot of the literature. Then we looked at susceptibility, and for whatever reason, we decided to measure it as a function of time. And we were a little bit disappointed to see. So we had the original susceptibility, then we squashed the rock, and we got a susceptibility there. And then we started measuring it. We ended up measuring it over a few months. And you can see there's quite a continuous decrease in susceptibility. And this was a little bit disappointing. And we weren't sure if this was due to a magnetic effect or due to, say, dislocations that were creeping or something. So we looked at different starting states from a magnetic point of view. So we AF demagnetized the sample. So I should mention these are all basalts from Iceland, just carrying the NRM. So we looked at ones with the initial NRM state, and we looked at ones that have been AF demagnetized. And it did seem to be a truly magnetic effect in the sense that the AF demagnetized ones, their response is very, very different to that, or less pronounced to that of the ones carrying the NRM. So that's some respect, that's quite good, because in nature you don't get AF demagnetized samples. So that's actually quite encouraging that it's more enhanced in the NRM effect, in the NRM state. So it seems to be a proper magnetic effect, and it depends on the starting state, but it does seem to depend on time as well. Now, in addition to that, we looked at started looking at AMS, and we weren't the first people to do that. Alex Kapitschka back in the 1980s did a lot of work on AMS and squashing rocks and seeing what happened. So what he has here, he has the AMS stereonet plots. This is the stress axis, here's the stress direction. This is the K1 term, and he's got little triangles. And as you increase the compression, it moves towards the center, move towards the stress axis. We repeated it in our samples, and we have our stress axis right in the middle. We're in the Z direction on our cores rather than in the X direction, but it's the same idea, is that you increase the stress, it moves towards the center. It's important that we're in the elastic zone. If you look at the literature, when you get into the plastic zone, when you start deforming the rocks, actually it moves the other way. The K1 term starts to move away from the stress axis. So it's important here, we are looking in the elastic zone of this effect. Now, one thing I was wondering, does the AMS fabric that we're inducing by applying a stress, is that time dependent? And it doesn't seem to be. I mean, the absolute terms of the anisotropy do change with time, but this rotation does not. Okay, now, I've been ignoring one of the things here. I mean, these are all like static experiments. And of course, we're really interested in dynamic experiments. So the difference between dynamic and static is that if you've got a static system, you squash the rock is elastic, and the rock has enough time to respond. So everything's in sort of equilibrium elastically. Whereas in a dynamic system, you squash it, and you squash it so quickly that the rock doesn't have time to respond elastically. And the effects can be quite different from a rock mechanics point of view. Now, people have done some work in the past. People have done a lot of work here, and it's very high loading strain rates here. So this is when you're looking at shocks and impacts and stuff. And a lot of work has been done over that in the years. But what hasn't been much work done is when you look at these much lower strain rates that we're interested in here, so 10 to the 2, this is more sort of earthquakes. This is the kind of values that we're interested in. So no one's really done many experiments apart from Nagata published a paper in 1971 where he had his bashometer, where he essentially dropped a ball onto a sample. And this is what I was asking David Dunlop about this morning over breakfast, if he knew anything about this, because he was in the 1960s, he was a postdoc in this lab, but he didn't seem to know, unfortunately. So he has this, the reason I asked him this question is we have this loading rate. So essentially it increases the loading rate and you get a change in the magnetization, which is kind of interesting for us. But of course, we're not quite sure how you achieve the change in the loading rate. If he was just dropping the ball from a higher rate, that would give a higher height. That would give a change in loading rate. But also, it would also increase the peak stress. So is this due to peak stress, or is this due to changes in loading rate? We're not really sure from the data. And this is the kind of strain rates that we're interested in. And this is the only study we managed to find that's done that. So that means we have to look at that ourselves. So I give you Nagata's bashometer, and I raise you UCL's The Thumper, which is an enormous piece of equipment. It's 4 meters high, and it's really quite intimidating. It's quite scary. But actually, it's actually much too big for what you need. So we went to Grenoble and used a much simpler setup. It's this long rod, put the sample in the middle, release a bit of air onto the pressure onto the rod at the top, and it moves along slightly. And we squashed the rock very, very gently, sort of, compared to the Thumper, which is enormous. And we only went a few weeks ago, so this is very new work. And this is something I took with my camera, slow motion. This is essentially the first experiment we did. So sending a shock wave from the side across. Our sample's just held in the middle by friction, and that's the experiment. Very exciting. You know, some people are putting man on the moon, and I'm squashing a rock between 2 metal rods. Sometimes I don't feel like I'm doing anything cutting edge science, but you know. And there we go. We got a little silver foil to capture the sample. Anyway, this allowed us to do dynamic stress experiments, which we think are important. And the question was, would we get the same results? And well, this is hot off the press. We only measured this last week. So we measured the initial starting state, then we went to Grenoble and squashed it. And then we have measured the state afterwards. And this is our result. We have more samples, but this is only literally just measured last week. So you can see that the peak stress is something we're interested about 100 MPa, so still in the elastic zone. And the strain rate is roughly the kind of value we're looking at for earthquakes. And you can see we're getting the same effect that we get with the static experiments, with moving the AMS, the K1 direction towards the stress axis. Okay. So just to finish up, so it's a bit incomplete in the sense it's still work in progress, but what we've discovered in the work we've done. So the micro modeling has shown that SV grains have the opposite response to stress, and also they're less stable, which kind of gives us this kind of paradox. So we now think from a thermal point of view, SV grains are more stable than single domain grains. That's from a micromagnetic modeling. But from the micromagnetic modeling of the effect of stress, it's actually single domain grains which are more stable. So which one is the more important one? You have to consider that when we're looking in zones with lots of fracturing and stress. And importantly, relatively low pressures of less than 100 megapascal potentially could be altering our magnetization. And then the sort of final part of experiments, which is obviously still very much ongoing, is can we use AMS potentially as a paleo stress determination? This is really the goal of the sort of bigger picture of what we're trying to achieve. So thank you very much for listening.
Do we have some questions? Ramon?
I'm curious about this kind of after effect that you have after you're having out of the stress. So you say you deform the rods in the elastic range.
Yeah.
So that would probably suggest that this is you induce some metastable magnetization, which is just viscosity decay. But is it also possible that you actually have micro damages in the sample, which you don't see in the stress diagram, but which are maybe diffusing after the experimental stage?
Well, that's a good question. So we're working on the line. It's due to some flipping into some metastable state. And we have discussed a lot about whether it's due to some microstructures that you can't see. I'm wondering myself if it's due to that effect. The fact that the initial magnetic starting state seems to have an important contribution to the response would suggest to me that even if it's not 100% a magnetic effect, it is a magnetic effect does contribute to that. So it's something that, it's a good point, it's something that can't be ruled out. Some sort of little microstructure changes that maybe the people who are doing rock mechanics don't care about because it's so much small, whereas in magnetics, you know, a little screw dislocation can completely change the response. So that hasn't been ruled out yet.
Thanks.
And so your samples are in a matrix, so your grains are in a matrix with other minerals
Yes.
with different viscosities. So the peak stress that the magnetite grain sees is probably different from the peak stress you're probably applying.
Very true, actually. I mean, I wasn't going to show this, but I have another slide. And this is from a completely different study. This is what we did with Roger, where we were looking at Martian meteorite, and the pressures here are much higher. But this is work done by my PhD student, Tom North. We had this images provided by Roger, and we were modeling the effect of stress, and we were looking at much higher pressures up at, 35 GPa. But the point is here, so these are the magnetic minerals, the black ones, and the point is the stress, the pressure and the temperature is not homogeneous. So yes, it does make a big difference. And this is something we'd like to work on as well. So we've been doing this for a completely different study, the Martian meteorites. We probably need to repeat this, and this is the plan, but on much lower strain rates, looking at something more like a basalt sample. So yeah, I think you're right. All the minerals do not have the same experience inside the rock, and it depends on things like grain size and etc. So to be continued.
I think also to depend on your host rock and what is the strain relationship to the different silicates that they're going to form, and how much that also takes in the stress related to the magnet.
Yes, I think it will do. Yeah, I mean, we've been looking at basalts because the magnetic is strong. Tom is very keen to look at granites, but I'm less keen to look at granites because the response is very different. Yeah, it's going to be very, very different. Yeah.
Just a technical question. Your increase of susceptibility as a function of stress, did you measure directional susceptibility, or so it's just mean susceptibility which cancels out the anisotropy?
Well, in this particular case, for these ones, yeah, this is just the bulk susceptibility. But then we did measure the AMS, and we do have the susceptibility in all directions for that. So we've done the similar experiments. So is that what you mean? Sorry.
Yeah, I would be interested how degree of anisotropy is increasing or decreasing as a function.
The degree of anisotropy increases as you increase the pressure. Yes. But that actually, so the direction stays, but over time that tends to relax a little bit as well. So the degree of anisotropy changes with time, but the direction of the anisotropy doesn't. And it's potentially, we're not sure, but if we wait long enough, it might just completely collapse and disappear. We've waited 3 or 4 months, which on a log time scale is, is quite long, but
I was just wondering whether this increase of susceptibility is not just increase of degree of anisotropy. You measure it on just one direction.
Well, that's why we moved from doing the bulk measurements to doing the AMS measurements, so that we could see. So there is an increase, particularly in the K1. So I mean, I don't have it with me right now, but the K1 increases as well, and other terms don't.
Okay, thank you.
Sure.
Hi, yeah, just a really quick question. So, the change in susceptibility, you see from a nearby fault, or from stress change from nearby fault. The real fault fractured many times, right? And there's many events that are accumulated over time. Do you expect the changes you see in the susceptibility to accumulate, or do you just see the biggest event? What do you think is the effect of having many events?
That is something we've discussed. So currently we're thinking it's going to be the sort of like the peak stress, the last one that was seen, but it could be more complicated than that if you've got, various events over periods of time which are overwritten each other. I'm not really quite sure what the answer to that one is, but yeah, I mean, ideally what you'd be looking for is like the last really big event. And we don't imagine this being a method that could be applied back millions of years, probably something, on a maybe slightly more than the human timescale, a few thousands of years, tying to geohazards. That's the kind of angle we're thinking about at the moment. Yeah.
Well, I wanted to talk to you about. So is it reproducible at different faults, this increase and then decrease in the susceptibility? Is it just something unique to this fault?
That's a good question. I can't answer that one. We've got the data for this particular fault, and we have written proposals to go back and look at other faults, but we haven't actually done the fieldwork yet. So until we do the fieldwork, I can't answer that question.
The increase is just really represented by points there in this one.
Yeah, and I'm not sure about, I didn't measure this, so it was measured, the data, I don't know what the change in lithology was. There could be a natural thing as well. But so that's why we were doing the experiments. So the idea was, well, if we can squash a rock and show it increases, it potentially could be that. So.
But the data changed from paleomagnetic cause, or was this in the field, pressing on the rock?
No, these were measured using Ellen Platzman's old Kappa bridge at UCL.
Okay.
So one of these KLY2s. Nothing wrong with those instruments. It was measured by a master's student or something.
Do you think if you used a handheld one in the field, you just walk towards the fault, you could get information about how that might be changing?
Well, that's would be the goal eventually, would be to either do something like that, or maybe even do a drone survey. If you could pick this up with I don't know if it's possible, but that's kind of the idea, that eventually that would be sort of the target. Yeah, but you're right, we need more field data. We've only currently got data from one fault.
Those are really good. This isn't a question or a statement, it's more of a, hey, you might be interested in some data. The US Geological Survey puts proton precession magnetometers next to faults, as well as volcanic centers, Long Valley, California, and they have historical data that's publicly available And what they were looking for is what they were calling piezo-magnetic effect.
Yeah.
And you would be able to potentially look at data immediately adjacent to a volcano as a new intrusion was being replaced, pressure regime, or kind of process fault. Maybe there's time series that would be useful.
Thank you for that.
I just want to make one quick comment. In a lot of the surveys we've looked at, faults often have a magnetic high, and it's often due to the fluid flow that's coming in.
Yeah.
So that's one of the complications. But they do map beautifully.
They do map. Yeah, there is a problem. You know, how do you unravel that problem? Is it is it due to fluids or is it really due to stress?
Well, you look at it in this section, you can write the reaction, you can see what came in, what was the host, what's the fault, what fluid.
Yeah.
John, can you speak up?
Yeah,
Julie's gonna.
really interesting work and glad to see you kind of taking this up again.
Right.
The other complication or thing that you should think about is that many times that these faults are actually what's in the fault zone is gouge.
Yeah.
So it's actually the accumulation of many faulting events.
Yeah.
And now when you have that type of rock and then you have another event and you have fault heating, flash heating, you have the potential to form new magnetic minerals. So when you're just looking at magnetic susceptibility, that's another issue to talk about. And there has been some nice work done on actual recorded faults in Taiwan that have made that argument.
Okay. Well, thank you for that. Now, I guess my response to that would be I have discussed this at great length about the heating effect, because obviously if you're right next to the fault, the heating, it melts the rock, so it can be very, very hot there. And I've been assured that once we get to more than a kilometer away, the sort of temperatures we're looking at, the variations are only a few degrees. So hopefully we're away from that zone where heating is an issue.
But can I just follow up on
Sure.
that? A kilometer away, that seems to be a tremendous mismatch in your experimental and the actual stress field.
Well, potentially depends on the size of the fault, doesn't it? I'm not sure. It could be. I mean, yeah, maybe we need to look at lower pressures. I don't know. We have a range of data. We just need to. I'm not sure at all. But something to think about.
I guess it's somewhat a follow-up from John's question. So if you have processes such as that near the fault, could the low magnetic susceptibility be due to this very fine grained single domain material?
You mean due to alteration of the? It could be. Yeah. I mean, these very low values just here. I'm not really quite sure what that point is, but I guess we're more interested in this decrease. I guess as we go further away, I think this part of the signal here probably, it's got a lot of other things going on, fracturing, plastic deformation, whereas we're further away, the peak we're interested in. This decrease here, we suspect, is really what we're looking at. Maybe should have said that in this section here, we're looking at the decreases, essentially the pressure as we get further away.
So I'm going to ask a really basic question. What causes the decrease in susceptibility in a physical model?
Well, I don't have a strong physical model for susceptibility. It's not something that's hard to model. I suspect the magnetization is being rotated into an unstable state, and when you look at the susceptibility, it's more able in the AC field. It's moving more and gives rise to a bigger signal. It's very hand wavy. You don't really have a firm.
So you AC susceptibility?
Well, it's kind of hard to do AC in a micromagnetic model because you've got this very high fluctuation. Well, we can do it. Yeah, we can do that. Yeah.
It was great. It's really interesting. I think if you can possibly tie this to, the paleo stress regime, it's fantastic. There's tremendous amount of interesting things. Oh wow, that just got 3 hands. We're going to do this quick.
Maybe I missed it. Is the lithology uniform?
In this particular case, I've been assured it is. Yeah, I don't know. This is another thing that really needs to be double checked.
Is it volcanic, Adrian, or is it? What is
Oh, this was granite, apparently.
Ken,
Just a quick question, what kind of fault is it? Is it a normal fault, thrust fault, spread slip? What's the strain field look like in that?
You've got me there. I don't actually know off the top of my head what I can find that information for you, but I don't actually think it's, I couldn't, I wouldn't want to say whether I could probably get it wrong. I'm not quite sure exactly which type of fault it is. I have to check.
take one more. Oh, just one follow-up. Oh, it's okay. It's fine.
I just want, I mean, also, if you're looking at AMS, you're looking at the paleo strain too. And I wonder how that, factors into this when you're looking at the whole wall.
I think the point is that they're in the elastic zone. So once you remove the, well, that's what we're trying to look at, the elastic zone. Once you remove the effect of the stress, that there's no strain left. The strain is zero. So there is no paleo strain.
Okay.
That's the idea. I'm not saying it's necessarily true, but that's what we're trying to working with.
Paleo strain indicators from AMS. So how do I? Yeah, never mind. Okay.
All right. Okay.
Okay. We can open up to other questions, other speakers, are there any? No. It's wonderful. Well, I guess then the question would be taking that one. Oh, online, sorry.
One quick comment from Win.
Wynne's very busy today, isn't he?
Win is.
I'm sorry.
Ooh.
Oh, do you want me to talk? Okay. No, it was just an observation from the comments really from the audience now, which of course I agree with. The only point I wanted to make was that, from the numerical work, at least, we do see that there is a clear stress-related signal from single vortex grains in these kind of stress regimes. So, given that we might expect there to be something from a release of stress or stressing and then releasing the stress in single vortex grains that hold a strong remnants, can we disentangle it from the other processes that people have mentioned here? It's just that comment.
Take it from that.
Okay, well, thanks, Adrian. And it is lunch